Deriving Avogadro's number from the diffusion coefficient. Our goal is to analyze how diffusion relates to Avogadro's number and determine how closely it models an ideal molecular diffusion by calculating sample values of Avogadro's number for polyester beads of 5 and 2 microns. Our calculated values were 2.9 times 10 to the 14th for 5 microns and 6 times 10 to the 14th for 2 micron beads. This means our situation is directed motion probably rather than diffusion. In our system scheme, the slide of the microscope exerts a normal force in the beads, the earth exerts a gravitational force in the beads, and there's a viscous force and drag force between the water molecules and beads. In our free body diagram, consists of many forces from many water molecules pushing on the particle, resulting in Brownian motion and random walk. This means that there are many viscous forces and many drag forces from various water molecules on the beads in various directions. Initially, the energy is all potential energy. When they're shaking the ball, considered some of this potential energy and kinetic energy. There's some internal energy from viscous and drag forces exerted by the water molecules. There's an overall loss in energy in the last state due to the resistive forces. Diffusion. For 2D motion, diffusion can be modeled by the equation x equals square root of 4 dt. X is the average displacement particle, t is the time elapsed, and d is the diffusion coefficient. Via tracker, x can be calculated and t can be found. Then d can be solved for and applied to the equation for an Avogadro's number.
Brownian motion is the random movement of particles in a fluid due to constant bombardment from all sides by the molecules in the fluid. Diffusion, unlike Brownian motion, is not random motion. It is the movement of anything from an area of higher concentration to lower concentration driven by a concentration gradient. Initially, we thought that a random motion of particles in a solution was due to collision with thermally agitated molecules, but the individual displacement was too small for each molecule, and because of this, we could not detect the smaller displacement present. We could only see larger displacements where all collisions push particles in one direction. Thus, the particles executing random walk can be modeled via diffusion and diffusion constant, r, which is the radius in meters, and Avogadro's number. We can rewrite this equation to calculate Avogadro's number.
So for our experiment, we had polystyrene beads with 2 different radii, 5 and 2 microns, and we placed them in water. We then observed the movement of the polystyrene beads under a microscope and recorded the movement. The movement of the individual beads in both the trials were recorded and measured via tracker. We then used this data to calculate the diffusion constants of the radii. And you can see here, this is our data from both of the trials. And then for the results, while we observing the video footage of trial 2 with the smaller beads, it is clearly apparent that the beads are traveling at higher speeds relative to trial 1, as can be seen with the data. It is unclear whether this is occurring directly as a result of the radius of the beads being smaller or the increased kinetic energy inside the water sample from the disproportionate shaking. But in both the trials, the beads appear to be diffusing from the bottom left to the top right of the
For trial 1, the average distance calculated was 0.435 centimeters over 0.463 centimeters, and for trial 2, the average distance covered was 0.296 centimeters over 0.177 seconds. Now, we used the diffusion constant formula to calculate the diffusion constants, and the speed was significantly higher in trial 2 than trial 1, so it makes sense considering that trial 2's diffusion constant is higher than trial 1's.
And the Avogadro's number can be found with gas constant times the temperature over 6 times pi times viscosity times the radius times the diffusion constant. And we calculated the Avogadro's number using the diffusion constants that we had. And we found Avogadro's number to be 2.90 times 10 to the 14 and 6.0 times 10 to the 14, respectively. These calculated values are significantly different from the actual Avogadro's number, 6.02 times 10 to the 23rd. And we will elaborate more on that in the flaw slide. And then because the observable trackable motion was not highly representative of the Brownian motion, the diffusion constants calculated from the data were artificially high from the speed of the particles, hence why Avogadro's number is so low relative to its actual number. And these large diffusion constants cause the calculated values of Avogadro's number to be very much smaller than it really is.
Flaws and limitations had a large impact on our results. Technological limitations, such as the camera on the microscope not capturing at a high enough frame rate, made movement hard to track. Trials 1 and 2 also likely started out with differing quantities of kinetic energy due to the length of time in which shaking occurred not being controlled. And although the beads can be considered microscopic, the beads are larger than the observed particles in most case studies regarding diffusion.